Hello, I welcome you all in this presentation related with the subject fundamental subsurface engineering, and we are talking about a technique wherein a layer of the required material is deposited onto the surface of the substrate so that the improvement in tribological life of the component can be realized. And under this heading we have talked about the various welding processes which are used for depositing the bead on plate so that surface modification using weld surfacing can be achieved. Now we will be talking about the another process which is called the laser cladding. This is also we can say the improved version of the weld surfacing wherein the laser is used. So, the process is laser cladding. You know, the cladding is used for depositing a thick layer of the material to be deposited onto the surface of the substrate for surface modification, and this can be used for building up of a layer, of the material matching with the substrate, This is one possibility. So, this can be machined out and we can regain the required size and shape. It can also be used just for developing a very thick layer of the material of the corrosion resistant materials, so that the tribological life of the component under the corrosion conditions can be enhanced. So, the fundamental approach of this process is that it uses the laser beam. Laser beam, we know that offers very high energy density, which may range say 10 to the power 3 to 10 to the power 10 watt per mm square. So, as per the need of the energy density, we can regulate it suitably, like for those applications where just heating is needed, we use the lower energy densities like 10 to the power 3, 10 to the power 4. Further, higher energy densities are used where fusion is needed like welding or the laser cladding. So, 10 to the power 5, 10 to the power 6 kind of the energy density is used, and for those conditions where ablation and the evaporation is needed for machining purposes, much higher energy density like 10 to the power 8 or more energy density is used. So, for for laser cladding where fusion is involved for processing like the welding and the cladding purposes, the energy density of 10 to the power 4 to 10 to the power 6 is a watt per centimeter square energy density can be used. There are various ways to adjust the energy density associated with this process. One is laser power and another is the beam diameter over which laser is applied, and these two parameters significantly help in regulating the energy density as per requirement, so that the fusion of the substrate and the filler metal or the material which is to be applied onto the surface of the substrate can be realized. There are two variants associated with this process. Here the laser beam is directed onto the surface of the substrate. So, this will be facilitating the fusion of very thin layer of the substrate here at this end, and to apply the material for surface modification there are two variants wherein the coaxial feeding of material means material in powder form is fed along with the laser itself onto the surface of the substrate, so that and this can be fed with the use of the suitable carrier gas like argon or carbon dioxide as per the material. So when it passes through the beam and then by the time it reaches to the surface of the substrate, the material which is to be applied is brought to the molten state. So it is melted and gets mixed with the substrate, and that is how it forms the cladding. Cladding is nothing like developing a thick layer of the material onto the surface of the substrate. So this is one approach where coaxially the material is fed coaxially or in line with the laser beam itself, and when it passes through the laser and by the time it reaches to the surface of the substrate, it is brought to the molten state, and then it mixes with the substrate molten substrate material to develop the required modified surface. Another approach is the pre-placement. So the material to be applied onto the surface of the substrate is placed with the in form of either paste, or it can be applied by the thermal spray process, and then this material is brought to the molten state with the help of laser. So laser beam is directed onto the surface of the substrate. This will be fusing the material already placed, and the substrate, the thin layer of the substrate will also be melted. So that's how the mixing proper mixing of the substrate material and the material which has been placed at the surface of the substrate is facilitated with the use of the laser beam. So these are the two approaches of applying the required material onto the surface of the substrate with the help of laser coaxially feeding of the material or pre-placement technique. Now since this process uses the higher energy density for melting of substrate and the filler or you can say the material to be applied. So because of this it requires very less heat for melting purpose, and we have very good control over the heat applied for this purpose, and because of the good control we find that the dilution is reduced. Reduced dilution reduces the possibility of the degradation in quality of the material being applied, and here the dilution is found even less than 1% in if the process is applied with very good control. So since the energy density associated with the process is high, and therefore it uses the less net heat input for the melting and developing of the development of the layer of the suitable material for surface modification, and because of this we find the high cooling rate during solidification. So a high cooling rate means solidification time is reduced. Reduced solidification time leads to the refined grain structure. The refined grain structure, this refinement means high cooling rate. If it is moderate, then we get the fine grain structure, but if the too high cooling rate conditions can also lead to the formation of the amorphous structure also. So we get both these factors will be helping to improve the mechanical properties, especially the hardness, and which in turn helps in improving the wear resistance of the material. Since we get the proper fusion of the material being applied either by the coaxial feeding approach or through the pre-placement technique and the substrate. So both are fuse together, and this in turn leads to the formation of the good metallurgical bond, and therefore there is no bonding issue which is commonly found in case of the thermal spread coatings. And apart from this, since the temperature increase is significantly higher than the temperature required for fusion, temperature rise may be like say 15,000 to the 20,000 degrees centigrade. So, such a high temperature will be making the materials being heated too reactive to interact with the atmospheric gases all around the molten zone, and therefore the protection of the pool or the molten zone which is being formed becomes important, and therefore this protection to ensure that the pool is properly protected, like inert gas shielding is used. Argon or helium, or for the ferrous metals even carbon dioxide can also be used for protecting the pool from the contaminations by the atmospheric gases. So, now if we see the advantages of this process, we can apply any kind of the material, because the heat generated and the temperature rise is sufficient to fuse any kind of the material, and that is why this can be effectively used for developing the corrosion resistant surfaces, wear resistant surfaces, as well as for surface modification of any surface whose surface modification of those components wherein we need just a buildup of the material for regaining the size and shape after the machining. And because of these excellent applications of the laser cladding, it offers certain advantages. So, laser cladding offers many advantages. These are primarily in form of the higher energy density, controlled heat melting of the substrate, leading to the reduced dilution even less than 1%. So, the good control over the dimensions dilution helps in improving the quality of the surface modification, because there is no degradation in the quality of the material which is being applied during the surface modification by laser cladding. Reduced heat input due to the higher energy density process reduces all adverse effects related with the distortion or weld thermal cycle, adverse effects associated with the weld thermal cycle or the residual stresses. So, there the problems associated with the weld thermal cycles or differential heating and cooling are reduced, and because of the excellent the fusion of the material being applied and the substrate, we get the very good metallurgical bonding between the cladding and substrate. So, there is no issue of the debonding or delamination of the layer which is being applied, and since the laser can be used for controlled melting of the material being applied and the substrate very effectively, that is why all those difficult to access surfaces where other methods cannot be applied, laser can be effectively used for surface modification of those surfaces which are direct in line of sight of the laser beam, So, those difficult to access surfaces which are having the line of sight of the laser beam can be easily modified with the help of the laser cladding approach. So, this is the another good advantage, because if this access of the surfaces is not easy, then surface it will make the job of the surface modification more difficult. Further, very limited, or we can say very controlled melting of the substrate. Like we may control the melting just half mm or 1000 micrometer. So, this controlled melting and then development of the thick layer of the material to be applied. So, the extent of the melting of the substrate can be reduced, it can be controlled very well, and this in turn will be facilitating the deposition of the material by the laser cladding, even the metallurgically incompatible material systems onto the surface of the substrate. So, very controlled melting of the substrate helps us to develop the weld surfacing or the laser claddings of the metallurgically incompatible materials also. So, this is the another advantage related with the laser cladding. And whenever it is applied, how it is applied, because the laser beam diameter is very small, and if the large area is to be scanned, then say we are using the pre-placement technique, then the material to be applied will be spread all over the surface, either in form of the paste or by the thermal spraying, and then after applying the material on the surface of the substrate, the laser beam will be scanning the surface one by one like this. So, the laser beam will be passed through the particular path, so that the fusion of the material applied on the surface and the substrate can be facilitated for the surface modification, and thereafter it will be tracking the another path like this, and normally between these two paths some overlap is used, and that we can see in this front view, where we see if this is one path which has been created by one pass, this is the one section which has been developed by one pass of the laser beam, then another pass is developed by overlapping the earlier developed path. This overlap may vary from like say the 25 to 50%, and this will help in having the proper continuity and the bonding between the various tracks and various passes which are being developed, and therefore some extent of the overlap is always used between the different passes which are being applied. As far as the parameters of the laser cladding is concerned, there are parameters like laser power and the laser scanning speed. So, this is the laser scanning speed, about the speed at which the beam is moved over the surface of the substrate, and the power is about the energy associated with the laser beam. So, how does it affect the quality of the claddings or the coatings which are being applied? So, like say the increase in the laser power will be increasing the amount of the heat being applied, and increase in amount of the heat being applied will of course be increasing the width of the cladding. It will be reducing the height of cladding because increased heat input will be facilitating the flow of the molten metal to the greater width, and the height will be reducing. At the same time, this will be increasing the dilution level. On the other hand, if we increase the laser scanning speed, increase in laser scanning speed will be reducing the width of the cladding or the laser cladding which is being applied, it will also be reducing the if the material being applied per unit length is reduced, then height will also be reduced. But if the material is same and if the speed, if the material is deposited in the same amount, then an increase of the speed due to the reduced fluidity, it will be increasing the height of the cladding. But for the same the flow rate of the material, or for same amount of the pre-placed material, the width of the cladding or height of the cladding will be increased. At the same time, the dilution will be reduced with the increase of the scanning speed. So, because when the for the given power, if the speed of the laser scanning on the surface of the substrate is increased, then actually it will be reducing the net heat input which is being supplied, and because of the reduction in the net heat input, this will be reducing the dilution, although it will be increasing the cooling rate. So, if the cooling rate, as I have said, is too high, then it will be leading to the amorphous structure. Otherwise, moderate cooling rates will be leading to the development of the fine grain structure. If we typically see the laser cladding cross section, then at the interface, like say this is the cladding which has been developed. So, this is cladding, this is substrate, and this is the cladding substrate interface. So, on approaching from like say this is the cladding substrate interface. So, initially normally we get the planar structure. Next to that, this may be very thin. This is of the planar structure. Sometimes it is absent also. Thereafter we get very fine cellular structure. This width may also be very fine, and thereafter we get the another layer of the columnar dendritic structure. These structures are very fine, columnar dendritic structure, and then we find the very fine equaxed grain structure as we move away from the substrate interface. There is a continuous difference in terms of the composition and in terms of the grain size, maybe in terms of the phases as well, and that is why we mostly find that there is a variation in the continuous variation in the properties from the substrate coating interface to the top of the interface. So, and if the protection of the pool is not proper, there may be some of the losses of the alloying elements from the surface region or near surface regions of the claddings due to the interaction of the molten metal with the atmospheric gases, and because of this there may be absence of some of the alloying elements, and this will be leading to the reduced hardness at the top layer, and that is why if we measure the hardness variation from the coating substrate interface to the top surface layer, then at this interface hardness is normally lower, then it will keep on increasing, and then near the top surface layer again it starts decreasing because of the loss of some of the alloying elements if the protection is not proper. So, maximum hardness we find somewhere at the middle or middle to the or the between middle and the top layer of the cladding. So, and this reduction is attributed to the loss of some of the alloying elements if it has not been there, and the somewhat lower hardness at the coating substrate near the coating near the cladding and the substrate interface, this is attributed to the dilution. So, the width of such kind of the hardness variations and the loss of hardness or reduction in hardness at the top layer, all these factors will be governed by the extent of influence of the atmospheric gases or the extent of the dilution which is taking place at the interface. So, we in both the cases, near the interface we get the lower hardness, and near the surface again we get somewhat lower hardness, while at the middle we get the higher hardness. So, the lower hardness at the coating substrate interface or the cladding substrate interface, this is attributed to the dilution, and the little loss at the top surface layer is attributed to the loss of alloying elements due to the interactions with the atmospheric gases or other impurities. If they are there at the surface maximum, we get just below the top surface layers, because here we have the limited effect of the dilution or limited effect of the loss of the alloying elements. And the typical materials, like there is one columnoid, which is basically the nickel base hard facing material. The cladding of this is deposited using the laser cladding of the columnoid, and whenever it is this is just for an example, whenever columnoid 5 coating or claddings are applied using the laser, it results in at the coating substrate interface, it results in the columnar dendritic structure, which is primarily made of primarily it is nickel, and between the dendritic arms we have the eutectic carbide mixture, and these are the prime components, and the heat input primarily be governing the dendritic, the size of the dendrites and the amount of the eutectic carbide mixture which is which is present in between the primary dendritic arm spacing. So, here like say this is the primary dendrite, these are the secondary dendrites, and there may be tertiary dendrites. So, between these the dendritic arms, this is the columnar, say this is the interface. So, this is the columnar dendrite, and between this we may have the eutectic carbide mixture, which will be, and these factors like the size, proportion of the various phases, means the average size, grain size of these micro constituents, and the proportions or the fraction of these constituents will be determining the mechanical properties and the wear resistance if they are developed by the particular process. And since the laser cladding offers the advantage of the higher energy density, low dilution, high cooling rates, and the effective protection by the typical environmental protecting approach like use of the argon or the helium gases, then it results in a very good quality laser claddings for surface modification. Now, I will summarize this presentation. In this presentation, basically I have talked about the fundamental approach of the laser cladding and why does it offer the good quality surface modification as compared to the conventional the weld surfacing processes. Thank you for your attention.